Hi all, it's Professor Marinos again. Over the last few weeks, we've developed concepts of equilibrium chemistry and of kinetics, and solved some small problems along the way. But I think with this dissolved gases lecture, we've really reached a point where we can start to synthesize these ideas into a complete understanding of how environmental chemical systems evolve over time. And today I want to do an example of that synthesis with you. And the way that I want to do this is I want to model the concentration of dissolved oxygen in a stream. So let's launch into that. By the end of this lecture, you should be able to use concepts from kinetics and thermodynamics to develop a simple model of dissolved oxygen concentrations in a stream. And then you'll be able to implement that model via a spreadsheet using the finite difference method. So to get into this, I hope I don't need to impress upon you the importance of dissolved oxygen. We all breathe oxygen. All organisms, besides a few microbes, consume oxygen in their metabolism. Here you can see a fish kill caused by the lack of oxygen in a water body. So the concentration of oxygen is a vital water quality parameter in environmental systems, and it controls a lot of the life that can happen in those streams. And as Matt talked about in his previous video, we have techniques that allow us to model the concentration of oxygen through time, or to measure the concentration of oxygen through time, and then develop a model of how much photosynthesis and respiration are contributing to the oxygen concentration in a stream. And so today what we're going to do is, if we look at this diel curve that we have shown down here, you can see the general pattern of oxygen concentrations throughout a stream. You have a peak of oxygen in around noon, when photosynthesis is really churning and light is shining down on the stream. And at nighttime, when there's no photosynthesis occurring, oxygen gets drawn down in the stream to lower concentrations. So you have this daily fluctuation in oxygen concentrations in a stream. And we're going to look at how to model that sort of thing mathematically and explicitly. So first, let's talk about our approach. Let's talk about the stage of what we're looking at. When modeling stream metabolism like we're going to do, our stream oxygen dynamics, often what we do is we define a reach of interest. And a reach is simply a length of stream that has relatively similar conditions along the entire length. So same amount of turbulence, same water flow speed, same amount of light getting to the speed. It doesn't have to be exact, but the better that these things are close to each other, the better your approximation of the stream will be. And we call this a reach. A reach can be 100 meters in length. It can be a few kilometers in length, depending on your system and how homogeneous your system is. Okay, and so within this reach, we can define a thermodynamic and kinetic system of interest just by drawing a box in the stream, bounding some surface in the stream. And, we can say this is our system. And this is obviously a very open system. You have a ton of water flowing in, you have a ton of water flowing out of this system at any given time. You also have exchange with the atmosphere. But what's important to note is that the change in concentrations of our species of interest of oxygen in this little box here is incredibly minimal from the inflow in the box to the outflow of the box. So if water flows out of the box and is replaced by new water, that new water is going to have almost exactly the same concentration of oxygen as the water that flowed out of that box. So, in other words, you have a situation where your inflows equal your outflows. And so the net change from water flowing in and out of the box is zero. So you can essentially, even though there's tons of water coming in and out, because the water coming in is the same as the water coming out, you can pretend that the total change of the system due to inflows and outflows is zero. And this is very useful because this allows us to just draw a cube around a volume of water in this stream, say a 1 meter by 1 meter surface area on the stream, multiplied by the depth of whatever the stream is at that point. And we can say this is our control volume. This is the volume of the system that we're going to model. And we're going to assume that everything that's happening in this volume right here also applies to every other volume in this reach, because this reach is homogeneous. So the systems are exactly the same in this reach. So from our reach of interest, we've defined a thermodynamic system that we're going to model, just a 1 meter by 1 meter square surface area on top of the stream, with the depth of the stream completing the volume of that system. So now that we've set the stage, let's move on to the players. We're considering the transfer of dissolved oxygen into the water and with exchange with the atmosphere. So there are a few reactions going on that we're going to consider. These reactions are, first, gas exchange with the atmosphere, dissolved oxygen becoming um, gaseous oxygen in the atmosphere and vice versa. So the water can always engage in bidirectional exchange with the atmosphere exchanging oxygen. And the direction of that exchange will simply depend on whether or not the water is oversaturated or undersaturated with respect to its oxygen concentration in the atmosphere. The second player that we're going to consider is heterotrophic microbes, or decomposers. And decomposers perform aerobic respiration, as we've covered before, taking carbohydrates and organic carbon, such as these leaves shown in the stream here, combining those with oxygen to produce energy, carbon dioxide, and water. So this is a reaction that consumes oxygen in the water column. By contrast, you have autotrophs, like algae, things that fix carbon, your photosynthesizers, who perform photosynthesis. They take carbon dioxide and water, and they combine those into carbohydrate, or structural sugars, and oxygen. So this is an oxygen-producing reaction. So these are the three reactions that we're going to consider happening in our system. We have gas exchange with the atmosphere, heterotrophic respiration, and photosynthesis. And the total change in oxygen concentration in our system with respect to time, so dO2 dt, is simply equal to the sum of the differential equations for all three of these processes. The sum of the change resulting from gas exchange, the sum of this differential resulting from photosynthesis, and the sum of this differential equation resulting from respiration. So if we just develop these three equations and just sum them all together for a given time interval, we'll get the total change in oxygen for a time interval as well. So how do we formulate these equations? Let's launch into this. First, we need to make some simplifying assumptions. The first assumption that we're going to make is that the temperature of the stream is constant. You know, this actually isn't true in real life because the temperature of the air changes and the water is in thermal equilibrium with the air. But for the sake of developing this simple model, we'll just say that the temperature is relatively constant. Secondly, we're going to say that the stream has a flat bottom on the bottom, just so that our control volume that we're looking at, our system, can be a rectangular volume, just for ease of calculation. Thirdly, and very importantly, we're going to say that the biomass of the microbes that do both the photosynthesis and the respiration are staying constant over the period that we're modeling. And of course, microbes are always growing and dying, and so this might not be a valid assumption that holds in your system, but over short time intervals, and let's say we're going to model oxygen concentration over 5 days, this is not a great, but an okay assumption to make, and to avoid some really, really hairy math, we're just going to say that the biomass is constant through time. The fourth assumption we're going to make is that the flow of the river is not changing appreciably. So we have constant flow in the river, and this means two things. One, our depth isn't changing, so our control volume isn't changing. And secondly, you'll recall that the reaeration constant is dependent on turbulence, and turbulence is obviously very closely related to how much flow is happening. You know, if you have a huge flow in a river, that's going to be like really churning up the water and mixing in a lot of oxygen. But if we just say that the flow is not changing appreciably, that simplifies our calculations a lot. So just, you know, standard flow maybe coming out of the bottom of a dam or something would be a good place where you'd see this sort of condition. Finally, we're just going to fix our day length at 12 hours. And why this is important will become apparent later. Okay, so these are the assumptions that we're going to make in building this model that make it pretty easily mathematically tractable. And you'll see how these play into our equations in a second. So the first reaction that we're going to consider is the gas exchange reaction. The exchange of gaseous oxygen in the atmosphere dissolving into water and vice versa. And this is an equilibrium reaction. It can go both ways. And the equilibrium concentration of oxygen, as we said before, is a function both of the partial pressure of oxygen in the atmosphere and the temperature of the water. So the partial pressure, this is just Henry's law, the partial pressure determines how much oxygen will dissolve in, and this will remain constant for a given elevation. So if you're at sea level, the partial pressure is going to be 0.21. If you're looking at a stream that's higher up in the mountains, say, the partial pressure will be less and less oxygen will dissolve into the stream. But yeah, it's dependent on partial pressure, and it's also dependent on temperature. But we said that temperature was going to be fixed. The temperature of the water is going to be fixed throughout the duration of our model. And obviously, the stream isn't going to move around. It's not going to go up high in elevation. It's not going to drop down in elevation, at least appreciably. And so the partial pressure of oxygen we could also say is constant. And this means that the equilibrium concentration of oxygen in the water is not a function of anything. It's a constant. And so this simplifies things for us a lot too. So the equilibrium concentration of oxygen is constant throughout the duration of the model that we're creating. How do we go about calculating this? Well, there are a few steps we're going to have to take. One, you'll recall that Henry's law constants are only valid for a specific temperature. And that temperature is normally 25 degrees. 25 degrees would be a very hot stream. So we're not going to use that Henry's constant. What we're going to use instead is a equilibrium constant that we calculate for the temperature of our stream that we choose using the Van't Hoff equation. You'll recall from previous lectures that this is the Van't Hoff equation. K at H1. KH1 is the equilibrium constant at your temperature 1, which is our standard temperature 25 degrees Celsius. And K at H2 is the constant that we're trying to solve for, which occurs at temperature 2, which is just an arbitrary temperature that we can set for our stream. So the first step to finding the equilibrium concentration of oxygen in our stream is to use the Van't Hoff equation to calculate the rate constant, or not the rate constant, the equilibrium constant that we're going to use. Then, secondly, we're going to use Henry's law simply to calculate the equilibrium oxygen concentration. Just a straightforward application of Henry's law using this K value that we calculated and the partial pressure of oxygen for our stream, or for the atmosphere above our stream. So, again, considering the atmosphere and gas exchange, we just described the equilibrium concentration of the oxygen in the stream. But we also need to consider the kinetics of gas exchange, because this gas exchange doesn't reach equilibrium instantaneously. And the kinetics of gas exchange, as Nick explained to us, is a function of this reaeration constant, this rate constant of reaeration, or this mass flux coefficient. And it's also dependent on the difference between the equilibrium concentration of oxygen and the actual concentration of oxygen in the stream. So, again, though, we said that the constant is a function of both temperature and flow. The reaeration constant is a function both of temperature and flow. But we said that the temperature of the stream was going to remain stable, and we also said that the flow is going to remain stable. So this reaeration constant is indeed truly a constant. It's not going to change over the course of our model. Although in real streams, if you have like variation in flow, if it's not like under a dam or something, this reaeration constant will change as the flow rate changes. But for our purposes, we're going to keep the reaeration constant, KO2, that is going to be a constant value throughout our model. And we said that the concentration of oxygen in equilibrium is going to be constant as well, because we're not varying temperature or the partial pressure of oxygen in the atmosphere. So this just means that the kinetics of gas exchange are simply a function of the current concentration of oxygen in the atmosphere. So we can just write this out as a differential equation. Nick gave this differential equation to us, and that is that the flux of oxygen, so the amount of moles per meter squared that is moving into a water body, so meter squared is the surface area of the interface between the atmosphere and the water. Or to express this another way, the change in oxygen, the change in the mass of oxygen with respect to time, or in the change of the moles of oxygen with respect to time, is equal to your mass transfer coefficient, or your reaeration constant, which we said was a constant, multiplied by the concentration of oxygen in equilibrium minus the concentration of oxygen that actually exists at any time. So the gradient between the equilibrium concentration and the actual concentration. This is your standard flux calculation, and this gives you the gas exchange that occurs in units of moles per meter squared of surface area. Now, to get to the change in concentration of oxygen, you've calculated the number of moles that are entering per meter squared, and you just need to take this equation and divide it by the volume. You know, moles per volume is a concentration. And so, moving on from that, we had this differential equation that expresses the change in oxygen concentration due to gas exchange with respect to time. Let's just put this in a finite difference method approximation. All we have to do is change these little deltas to big deltas and move the dt over to the other side. And we have an equation that expresses our finite difference approximation of this differential equation that controls the change in concentration of oxygen in the water due to gas exchange. Okay, so this is the final equation that we're going to end up using in our spreadsheet, or this is one of the final equations. Let's develop the other two right now. The second equation that we're going to develop is the consumption of oxygen, so the removal of oxygen from the water due to aerobic respiration. So microbes decomposing organic matter in the water using oxygen and producing carbon dioxide and water. You know, fish and stuff also do this, but their contribution is honestly pretty negligible to the overall water concentrations of oxygen. And to take this approach again, the kinetics of respiration are a function of temperature and biomass. I have never explained this to you before, but these are two important functions. As temperature increases, respiration of microbes increases. And as the biomass of microbes in total increases, the respiration also increases. You know, each microbe has a set respiration rate, and if you have more microbes, they're all respiring more. But again, we made two assumptions. One, that the temperature of the system isn't changing, and two, that the biomass of the microbes aren't changing. And so the rate of respiration in the system is constant. It was a function of temperature and of biomass, but if those two are constant, then it is also a constant rate, and it's a zero-order rate. And so if we want to develop the differential equation for this, we just say that the change in oxygen due to respiration with respect to time is seemingly equal to negative times some constant. We're going to call this constant kresp. And again, to put this in finite difference form, taking this infinitesimal differential equation and changing it into finite time steps, we can just say that the total change in oxygen over a given time interval due to respiration is equal to negative the respiration constant multiplied by the finite change in time. So this is the second equation that we're going to use in our spreadsheet to develop a model of dissolved oxygen in a stream. Okay, the last one that we're going to consider is perhaps the hardest one to consider. And this is the photosynthesis of oxygen. So the production of oxygen in the stream due to the uptake of carbon dioxide and light and water. This is performed by algae and to some extent plants that live within the water submerged but photosynthesize. And just to state the kinetics of photosynthesis, this reaction is dependent on temperature. Photosynthesis, like most biological reactions, is temperature mediated. The biomass of photosynthesizers that exist in the system, so all the algae and plants, and the amount of sunshine that's hitting that system. And again, we said that the temperature of the system is constant, and the biomass of all the algae and photosynthesizers in general, we're also going to hold constant for this model. So the kinetics of oxygen production via photosynthesis are only dependent on the amount of light that's hitting the stream at any given time. So that means that the kinetics of photosynthesis we can model as perhaps a first order rate. It's not truly a first order rate, but it's a good enough approximation for this model. We're just going to use a first order rate law to relate the production of oxygen via photosynthesis to the amount of sunshine that's hitting a stream. And so to write out this differential equation, we'll just say that the change in oxygen due to photosynthesis with respect to time is equal to some rate constant, the K of photosynthesis, multiplied by the amount of sunshine that's hitting the stream, so the amount of light. And again, to express this in finite difference approximation, we'll say that the total change in oxygen over a time interval is equal to the rate constant of photosynthesis multiplied by the amount of sunshine that hit that stream over that time interval, multiplied by the change in time, or the time interval that we're going to use. Okay, so now let's consider sunshine. How do we model sunshine? Well, it's not exactly a very clear thing how you do that, but I mean, let's look at this little plot that's kind of a cartoon that explains this a little bit better. Um, so net irradiation is just a fancy scientific word for the amount of sunshine that's hitting a place. And as you will certainly intuit, at sunrise it's pretty dark. Then as the sun rises up in the sky, you have more and more light hitting a place until noon, where you have the most amount of sunshine. And then this decreases until you reach sunset. So if the sky is clear, you have this nice arc shape that almost looks like a sine wave, or the top half of a sine wave. But you also have clouds. And clouds intercept sunlight and reflect it back to the atmosphere or diffuse it. And so if you have clouds passing over an area, your actual measured sunshine at a given place is going to be less than the total amount of sunshine that's coming in from the sun at that time. So under clear sky conditions, you have this nice, beautiful arc, but under cloudier conditions, you have this lower level of sunshine. And you notice this graph only covers a period of sunrise to sunset. Obviously, between sunrise and sunset, you have no net irradiation on your land surface. So we need to account for all of these factors when we're going to produce a mathematical expression of how much sunshine is hitting an area at any given time, such that we can model photosynthesis. And so I'm going to build a simple sunshine model. Just stick with me a little bit. We're going to base this off of a sine wave, and then we're going to relate this back to the production of oxygen via photosynthesis. So net irradiation is a function of time of day. Obviously, we just explained that. Latitude, obviously at higher latitudes, you get less sunlight than at the equator. The day length, which is a function of the season, and the number of clouds in a system. This latitude, that's fixed for our stream reach. The day length, we're going to model a short enough time that we can just say that the day length is essentially constant for the duration of our model. And so all we need to do is have net irradiation or sunshine be a function of the time of day and the clouds that exist in the system. How can we make a function that does this? Well, like I said, this curve here kind of looks like the top half of this sine wave right here. And so we kind of want to use that perhaps as the basis for our function to model irradiation on the land surface or on a water surface. And so this green line here shows the function y equals sine t, where t is in hours, or t can be any units for this equation. But your classic sine wave goes between 0 and 1, and it has a frequency of 2 pi. So the sine wave completes one cycle every 2 pi. But if our time axis is in hours, that's obviously not what we want. We want this to repeat every 24 hours. So we want a hump in the middle of the day that is our sunshine that comes in when the sun is up, and then the sun rises the next day at exactly, say, 6 o'clock in the morning. So the sine wave is a good start to base our sunlight model off of, but we need to do some transformations to it to get it to actually reflect what light conditions look like in the world. So how can we do that? Well, we can just do some basic bending and stretching and shifting of your basic sine wave to arrive at a hump like this, which has the maximum at 12 hours, or noon, and which is stretched out such that it repeats itself every 24 hours. And the way that we do this, you don't really have to get bogged down in the math if you don't remember this from your trig classes in high school, is that first we're going to change the frequency by multiplying the variable by some constant. So I multiplied it by 2 pi and divided by 24. And we want to phase shift it because the sine wave starts at 0, it starts going up. But if time 0 is midnight, and I just want to set time 0 as midnight arbitrarily because that's just the clock time that we use, I need to shift it 6 hours into the future so that the sun rises at 6, so that the light starts becoming positive at 6 and not at midnight. So that's what this -6 does. This changes the frequency. This shifts the phase of the sine wave. And then finally, signs are bound between 1 and -1, but irradiation is not bound between -1 and -1. So we can put a constant out front here that changes the amplitude of this sine wave. So here I just put in 3 for demonstration purposes, and that's what we can use going forward. So this sine wave is stretched out longer. It has a much greater frequency, has a greater amplitude, 3 times the amplitude, and it's moved over 6 hours to the right. That's what this equation here does. You don't have to get bogged down in the details of this. Just use this equation. But you'll see still that what we have going on here is that we have negative irradiation values predicted here, which obviously is not what we want. We want the sun to rise at 6 o'clock and have this be the light that is present from 6 a.m. to 6 p.m. We're just going to set a 12-hour day length. But at nighttime, we don't want to predict negative irradiance. We just want to have it be 0. So the way that we can do this is just say, let's take the maximum of this sine function that we just said, or 0. And so when this goes negative, the value of y just becomes 0. So now we have this nice hump-shaped curve that represents the sunlight during the day, and during the nighttime we just have 0 irradiance, or 0 irradiation shown here. And so this represents quite nicely this figure that we've shown here if they had extended it out to show 0 sunlight during the night. But we also said that we need to take into account clouds. How can we take into account clouds with this model? Well, what I would propose that we do is we just say that in any given hour, and we're going to model this on an hourly or half-hourly time step, clouds intercept some percentage of light in the system. And so the amount of light that makes it through is simply 100% minus that percentage of light that's intercepted by the clouds. And clouds kind of drift randomly across the sky, not totally randomly, like, you have fronts of weather moving in and out, but for the sake of this model, let's just say that they're random. So what I would say that we do is we can simply multiply this entire equation that we just generated by some random number that's between the lowest amount of light that might be intercepted by clouds, and 1. And this 1 represents 100% of light transmission. So, clear skies, 100% of light is getting through. So if we just generate a random number, and I said that this u means that it's a uniform distribution of a random number, so just picking any random number on the number line and pointing to it, between some lower bound and some upper bound of 1, if we multiply this function by this random number, you get a nice sine wave that has some random noise interspersed on top of it that represents the interception of light by clouds. And this, I think, is a pretty great light model for the purposes of this class. You can see this recapitulates this pretty well. This is also just a cartoon. But I think that this light model will do us a very, very good job of modeling our net irradiation to the stream. And we can use this net irradiation value again to simply multiply it by the constant of photosynthesis, the rate constant that we set, and we arrive at the net change in oxygen due to photosynthesis over any time. So just to lay out all the equations that we're going to use in our model, we're going to have the calculation of the oxygen concentration and equilibrium in the stream that simply obeys Henry's law, and we're going to determine the constant K via the Van Hoff equation. We're going to use this sort of ugly equation that we just developed to model the net irradiation at any time of day in the system. And then we have these finite difference approximations of the differential equations that we developed. This equation represents the change in oxygen concentration due to gas exchange. This represents the change in oxygen concentration due to respiration. And this represents the change in oxygen concentration due to photosynthesis. Taking this net radiation term in from there, and this O2 equilibrium term fits into this equation here. And then, to get the total change in oxygen concentration over a given time interval, we just sum these 3 differential equations up, and we can approximate the oxygen concentration. So, in the next video, I'm going to take these equations, and we're going to stick them into a spreadsheet. And this is a problem that we're going to look at. Let's say you've gone out to a stream and measured the following parameters about the stream. Model the dissolved oxygen concentration of the stream over 5 days using these data. First, we have a mean river depth of 0.5 meters. We have a temperature of 12 degrees Celsius. We have a maximum daily sunlight intensity of 3,600 watts per meter squared. And you don't have to ascribe any meaning to this value. This is just going to be the constant that we multiply the entire sine function by to change its amplitude, so to make the sine wave taller or shorter. We can say that, it's a partly cloudy 5 days that we're looking at, and so that the light penetrating the clouds is between 60 and 100% of the total light that's coming in from the sun, just chosen at random for any given time interval. And the concentration of oxygen at midnight I'm going to provide for you in the spreadsheet that we're going to start. So we're going to say the time 0 is midnight, and I'll provide you a concentration of oxygen at time 0 that you can just say that you went out and measured. Finally, we need these rate constants. You have the gas exchange constant, you have the respiration constant, and you have the photosynthesis constant. And with all of these, we have all the data that we need to model the change of oxygen in a stream. And one point that I want to make is that normally when you're doing stream biology, you're modeling the inverse problem of this. What you do is you take dissolved oxygen measurements, and from those dissolved oxygen measurements, what you're interested in finding out is perhaps how much heterotrophic respiration is happening in that stream, how much photosynthesis is happening in that stream. So normally you're starting with this value known, and what you're trying to do is you're trying to back out these values here, and by that back out these K constants, which tell you something about the biological activity and the gas exchange that's occurring in the stream. But for the purpose of this model, we're going to do the forward problem. We're going to start off with these constants, and we're going to calculate the change in oxygen in the stream over a given time interval. So in the next video, we're going to do that in a spreadsheet, so let's just jump in.